Hey Logic users, you want to run more plugins, you want to master on the fly, and you want your system to run stably without system overloads or interrupts. How do I tune Logic settings to get the absolute best out of my system? If you run Logic Pro, this is for you. If you run Logic Pro on Apple M1 systems, this is definitely for you. My name is Mark Payne. I'm a live sound engineer and producer working here in the UK. Let's go. So we're going to split this into 6 sections. In the notes below, I'm going to give the timestamps so you can jump around, but I really suggest you come with me on the whole journey throughout the discussion. In section 1, we're going to discuss how macOS assigns process to processors. In section 2, we're going to look at the Apple M1 system and both the Icestorm high efficiency cluster of CPUs and the Firestorm cores for high performance. In section 3, we will load our benchmark logic session and look at how the CPU is utilized while it's running. In section 4, we're going to add more and more plugins to chew out the cores until we form system overload. In section 5, we will tune the audio settings of Logic to make best use of the system resources. In section 6, we will conclude and bring together our ideas for how we tune Logic to run the most complex sessions without interrupt. We will also be able to conclude and advise the difference between running an Air and a Pro version of the Apple Macbook, and maybe how this would compare to running a Mac Mini M1 machine. In section 1, we're going to talk about processes and processor affinity. Now, a programmer developer knows that their application is going to be run on a multi-core CPU. So they take the one application and they write it as multiple threads so that the threads can be distributed across all of the CPUs to get best possible throughput. A program developer cannot know in advance what the specifications of the machine that's going to run their application is capable of. For example, my iMac Pro here has got 10 cores, but it supports hyper-threading, so there's 20 cores there. Whereas my system on chip M1 machine has got 8 cores, and some of them are the slower cores and some of them are faster cores. So how can the application developer know this? Well, the answer is they can't. It's the job of the operating system to assign the threads to the cores. Now, sometimes you want threads to run on the same CPU. You might have a single channel that's got multiple plugins, and those plugins will create separate threads within the Logic Pro system. It would appear to be sensible to spread those threads over the multiple cores. That's not necessarily the wise thing to do, because these threads on a single channel have got a lot of commonality. They basically want to be manipulating the same data, and because that data lives in the L2 cache, which is closely associated with a processor, you can see that for a single audio channel, it's likely that we want the threads for those particular plugins to all run on the same core. Otherwise, we'll have to be juggling the data and sending it from one CPU to another CPU just so that we can get the process chain done. Because of this, we talk about this concept of processor affinity, where the application developer can say, I would like these to run together and these to run separately, if at all possible. This is done through the syscontrol call. There are no syscontrol calls that allow a developer to nail a process to a processor, but there are calls that allow certain processes to be grouped together and other processes to be grouped somewhere else. We can pre-advertise our desire to how that load is spread over the CPUs. The actual one-to-one relationship of the thread and the core is always made by the operating system. In section 2, we're going to look at some practical demonstrations of CPU load. Now let's just review the M1 machine. Effectively, it's got, if you like, 4 high performance cores. Here's 4 Kings, you know, they're high performance core cards, and it's also got for high efficiency cores, which are of lower processing power. This is the Firestorm cluster. It's a cluster of cores which are high performance, but they use more energy. And this is the Icestorm cluster. So if you're just using your basic word processing or you're reading your mail, you don't need to be using the heavyweight cores for that. You can play your lower value cards and get away with using less energy. So 8 cores in total, 2 clusters. One of the advantages of a system on chip is that these cores, these clusters, share L2 caches. So these guys can access the same high-speed memory shared between them without penalty. This gives us a lot more flexibility with processor affinity because we can spread with confidence different processes over these processors because they are sharing the same L2 cache. Now, it's not obvious. In fact, I'm going to say more than that. It's very unobvious which cores are which. We can see the overall processor utilization here is only around 10%. If we look at application monitor, we can see that around 6% is user process, that's programs that I'm running, and around 3 to 4% of it is system overhead, the operating system running. Although this machine is doing nothing, it's still running QuickTime, which is doing background screen recording. So it's not true to say that there's nothing going on. And in fact, you can see here that the screen capture process is using 31% of CPU. Now, that's not 31% of the whole of the CPU resource, you know, the whole of the eight cards, if you like. It's 31% of one of these single cores. So to start the CPU stressing process, I'm going to run the yes command, and I'm going to output redirect that to /dev/null and put that in the Unix background. Basically what that's done is it's just made a process which is just wasting time by saying yes, 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 and throwing that in the bin. It is using 98% of CPU, 98% of one of these or 98% of one of those. Now, I don't know. Let's have a look. Let's see if we can tell. My guess is a bit on 3, a bit on 4, a bit on 5 and a bit on 7. Now, even though you can see that it's only a single thread, the operating system is choosing to run it in multiple places. Why would it take a hungry caterpillar and decide to just keep on hitting a different CPU with it? Well, it spreads the load. Maybe that's a thermal thing. Maybe if you were a program that was already resident on one of these cores, it would be very disadvantageous for you to have your core completely obliterated by one program causing pain. So maybe we spread the pain. So let's carry on and make this even worse by actually introducing 4 of these things. Now it starts to become clear which cores are being dominated. It is in fact cores 3, 4, 5 and 7. Now if you listen carefully, the fans are running. On iStatistica, in fact, the fans are now running at 5,000 RPM because we are starting to warm the processor up. So 3, 4, 5 and 7 are the Firestorm cores. 1, 2, 6 and 8. They are the lower performance but lower energy Icestorm cores. You'll notice that although it's 50% of the cores have been utilized, we've still got notionally 50% left. But that's a bit of a misleading figure, isn't it? Because if you're a card player, and I play cards in my family, we've already played the big cards. So although it's 50% of the core resources, it's certainly not 50% of the power of the CPU that's left. So be careful when you're looking at CPU utilization, because the percentages won't always tell you the truth. Okay, so let's kill off this ridiculous CPU load. And you can see now that also the CPU fan is starting to slow, and obviously the machine will cool. So section 3, we're going to benchmark the system with a logic session that I've been using in some of my other demonstrations. I've just had me dinner and I've got a glass of wine now. So it's got to be 6 o'clock somewhere in the world if you're watching out there in YouTube. So if it's an appropriate time for yourself, pour yourself a glass. What's going to happen now is I'm going to think that my YouTube delivery is going to improve, but in actual fact it's going to get worse. But there we go. So let's have a look at what's going on. I've got an empty logic session. section, we can see that the machine is not busy, and I'm running the performance monitor. So the performance monitor comes by clicking on the CPU bar, and then you can see that we've got 4 cores in use. Now, the default behavior, 4 cores in use, the default behavior of Logic is to, on an M1 machine anyway, is to only use the 4 performance cores, the Firestorm cores. The idea being is there's no point using the low performance cores. We might as well leave those for something else, and I'll be discussing later on whether that's a good idea and whether there's any benefit to using all of the cores. So you can see nothing going on in the machine, not really any CPU activity, and nothing measured on the performance monitor from Logic's point of view. So let's load the machine up with some of those pointless yes going to dev null processes, and our general behavior is to start 4 of those to really get some load going. We know by testing that these are going to go to the performance cores. Okay, so what we can see here is even though the 4 cores are now very busy with the load of that yes program, the actual fact Logic is registering no busyness, if you like, in its Affinity queues. And the reason for that is because there are no plugins, there's no DSP load, there really aren't any tracks. So Logic isn't busy, but the machine is. And what this reinforces is that these performance meters are not telling us how busy the machine is, but really telling us how busy Logic is. And those two things are very, very separate. And that's really why you don't really want to be running other programs at the same time as you're running Logic, because otherwise it will make bad decisions on how it tries to load up the Affinity queues. If you're drinking along with me, so then have a little sip. We've opened up a real session, which I'll just get running in the background, just so that we check in that that's going to work fine. And let me just check on my own cans. Yeah, that's okay. That's running in the background. And this is Logic out of the box, standard settings, using the 4 performance cores. You can see that the loading of this session is reasonably high. I'm using all my favorite plugins. I'm mastering on the fly. I'm running 96k session. This is as I've proven in a lot of my other tests in this playlist of Logic running on M1 machines, I've shown that there is no way this session runs on an Intel MacBook Pro of any description in the 13-inch kind of world. It would run on a 16-inch Intel machine, but no chance on a 13. So I've already discussed that, and I don't want to go into that whole thing again. But here we're running with, you can see our Affinity queues are just over 50% utilized. We've got reasonable busyness in the high performance cores, and the machine thinks that it's in some way 36% utilized. We've probably used pretty much half of all of this resource we've got available to us, and you can see that kind of utilization on the CPU history, which is part of Activity Monitor. Let's have a look at those settings together, and let me just introduce them. And if you go to preferences and audio preferences here, so the settings that we're going to consider in the rest of this session are going to be changing the IO buffer size, talking about the processing threads, and how many of the threads we're using at the moment. We're defaulted to the 4 high performance cores. We're going to look at the size of the processing buffer, which by default is medium. We're going to talk about the multi-threading option of whether we're optimized for playback and live tracks or playback only, and the default is, as you see, playback and live tracks. And together those things really are the things we can manipulate to optimize how Logic runs in playback. Now, I will say that trying to relate these 4 Affinity queues to the 4 CPUs is a pointless task. There is no one-to-one relationship, because remember that the operating system macOS is a variable here and has the ultimate responsibility to assign an Affinity queue to a processor. So in this 4th section, we're going to look at loading up Logic with more and more plugin load. To do this, I'm going to use an example of a very expensive plugin, which is the Abbey Road Reverb Simulator from Waves. Now, I'm not blaming the plugin. I'm not down on this plugin. I don't happen to use it very much. What's important here is that you know just how hungry the Abbey Road Reverb is. I've created in 9 instances. They're on auxiliaries 18, 19 and 20, and I've put 3 plugins per auxiliary, and I can turn this plugin on. And what I want to show you is that in doing that, the Affinity queue really hasn't changed that much. Add a second one of these on another auxiliary. I'm telling you that this is an expensive plugin, but not a lot's going on here. Over here, I've happen to have kick and a couple of snares, which I've opted to assign to those sends. You can see that they're going to 18, 19 and 20, but the sends are turned off. But watch what happens when I turn one of the sends on. So here's 18 going on, boom, a bang. Look at the CPU utilization, and now we've jumped up to 43%. And now let's turn on another audio send. We're now at 48% overall utilization. And my point is this, listen, never watch me talk about Final Cut Pro X with any authority. I use it for editing this kind of thing, but I don't, it's not my profession. Audio is what I do, and Logic is certainly when I'm working in the studio what I do. And I get really bored of these kind of YouTube demonstrations where people are trying to prove benchmarks using 70 tracks of audio, which is a same copy of some sine wave or anything or something. It's not rooted anywhere. And they're not using the machine as a mix engine, and it just makes no sense. It's not a quality metric because it has no relationship to how you and I are going to use Logic. Stop watching those kind of YouTube things where people going, oh, and I could add 72 tracks to this. Hopefully what I'm showing you here is that sometimes plugins don't apply the CPU load until you actually route audio through them, because you may be automating the routing of audio in and out during the length of your session. So this CPU load, it's a dynamic changing thing as the parameters of our mixes change, and that's why Logic requires CPU headroom. You can start a session and then suddenly later you might see a system overload that you weren't expecting. Well, maybe it's because you've opened up an audio stream where you're routing maybe to an aux and nothing else is going in that direction. So now let's come back to the setup where now I've opened up auxiliaries 18, 19 and 20. Get things running, 40 odd percent CPU. We're balancing around that 50% just over within the Affinity queues. Now let's turn on the first plugin. So let's not even think that one reverb is one thread. One plugin is one thread. The plugins themselves might be multi-threaded. Let's open up another one. And you can see again, the Affinity queues have become even busier. And now let's open up a third one. Now we've seen, you can see here that Logic has aborted on a system overload. What I should do is give Logic another go. Okay, it aborts. Let's let it run again. It's running again. We've come up with an Affinity queue balance, which is not sending the system over the edge, if you like. So I've managed to get 2 of these Abbey Road reverbs added, and we're on the ragged edge of this not working. I'm going to suggest to you this ain't going to run a third one, but let's try. Oh yeah, we've managed to run a third one. No, system overload. So let's stop it and try it again to see if it can find an Affinity queue balance which will work throughout the CPUs. We're almost giving Logic a chance to rebalance its load, and then the operating system a chance to assign that to the cores. And at the moment, looks like it's working. Oh no, it's just gone. So 3 instances would appear to be definitely over the edge, 2 instances maybe. That's the benchmark that I wanted to draw for the standard settings as Logic comes out of the box when we're really pushing into the maximum plugin load. So in this next section, we're going to look at tuning some of the audio parameters that we have available to us within Logic. You'll notice that I turned off all of these hungry Abbey Road plugins. Now let's talk about some of these options. So if you go to Preferences and Audio Preferences, we're going to talk about the options that we see within this panel here. So when you see a system overload, one of the first things it will say to you is that you might want to consider increasing your I/O buffer size, and this is this setting here, which at the moment I have set to 1024 samples. Mostly I record live, so if I'm recording I will max that out. I want to use maximal buffers, which is the safest I can be. I don't really care about latency. It says here that this is going to give me a total latency, a round trip latency from input to output of 26 milliseconds. Now, if I was trying to play and record, listening to that in my ears, it would be almost impossible. 26 milliseconds is not, I can't integrate that as the same event as what I'm doing. So you could never record with that degree of latency if you're trying to play along to what you're playing back. But if you're tracking, then there's no good reason to not max this and make your recording as safe as it possibly can be. Now, I'm recording blind, of course. My digital consoles come into the mic preamp. They go through the A to D conversion stage. I take a split at that point, and it's that direct split of the mic pre digital signal that gets recorded. My live mix is then hits the console and gets processed, but what I actually record is the clean feed from the mic pre. But I wanted to say that this really has no impact on memory at all, because 1024 samples multiplied by 24 bits is 24k bits, but we need to divide that by 8 to get it into bytes. That's 3k bytes per track. Well, if I've got 3k bytes per track and multiply that by, let's say there's even 72 tracks being recorded, we're talking about a total of 216k maximum for that buffer. And of course, in memory, for a program that's already 4.7 gigabytes, 200k is nothing. It's not even measurably interesting. So really, for playback, tuning this parameter of the I/O buffer size is going to really achieve nothing. Really, it's a tuning for recording, which is basically biasing off risk versus latency. So next we're going to talk about this process buffer range. It's the size of the buffers that we're using for processing DSP. So the bigger the buffers we make during playback, the more data we can put in there. We're increasing maybe playback latency, but we really don't care about that. You can see that at the moment Logic is using 4.57 gigabytes in memory. Let's change this to be a large process buffer range. Apply that. So we've started Logic again, and we're going to have a look at the size of Logic in memory, and we're now using something in the order of 4.59 gigabytes. So this is using slightly more memory, but in the size, overall memory profile size of the machine, it's no big deal. So I see no good reason to not run it large, and we'll carry on with this discussion then. The performance impact in being able to run more plugins with this larger buffer, well, let's see. We couldn't really get beyond 3, and 3 wasn't stable, and I need to run it for a bit longer just to be sure. And at the moment we seem to be running 3 okay, and I want to give it a bit longer, and I also want to maybe stop it and restart it to be sure. And it would appear that 3 is running reasonably reliably. And if you remember before, when we had the setting down at medium, 3 was a struggle. And you'll notice that we've got audio here, so we can't blame the fact that I've not rooted. I definitely have rooted 18, 19 and 20 is live. That would appear to be running 3 with stability of the additional plugin loads. Let's see what happens when we go to 4. No, 4 bombs it out. Let me take the 4th one away, restart it. Yeah, you'll remember that 3 was on the ragged edge, and now I've not had a problem running 3 at all. So running a large buffer size improves performance. We can now run reliably the 3rd copy of our heavy Abbey Road plugin, whereas before we could only run 2 reliably and 3 was on the ragged edge. Let's talk about the next one, the multi-threading policy. So what Logic is doing is it's preserving a degree of CPU headroom for the recording of additional tracks, or in fact the live input from maybe a keyboard to a software instrument, to make sure that none of your playing or additional recordings are lost during the session. We reserve some headroom in CPU to ensure reliability in that area. We have the option of turning off that protection to benefit only the playback tracks. So in setting that and applying it, let's see what happens now when we run the session. We are successfully running the 3. We have this stable situation now where we can run 3. So let's try and add a 4th. And no, that sends us over the threshold. Let's allow it to rethread that. No. And another time. No. And let's turn back to 3. Yes, that is running fine. Allowing it to the CPU power to be dedicated to playback really hasn't made that much of a difference. It's not made it worse, but it's not made it any better. So the final part of this tuning is to now allow the M1 machine to have all 8 of its cores used. So in this situation, you can see that the automatic, the recommended setting is only use the Firestorm cluster, you know, the high performance CPUs, 4 CPUs, which is why we see these these bars here. Now, why don't we max that out and say, well, why don't you use all 8 of the cores? So you've got, you know, the Firestorm and the Icestorm cores available to you. And in applying that, when it restarts, instead of the 4 cores being available, there's now 8 cores. If we now run the session and allow it to stabilize out, you can see that really we've been able to actually spread the plugin load wider over the 8 cores, and so the overall Affinity thread loading, if you like, has gone down. So maybe this will give us the opportunity to load the machine up with more plugins. Well, there's the 4th one that we couldn't run before, which is now running fine. And there's the 5th one gone in, which again is running fine. Now I want to stop this and restart it just to see if I have any problems with the reliability of Logic on the fly, but that would seem to be fine. And then here comes the 6th one, which is running. So we are successfully running now with 6, and we couldn't get beyond 3 before. And you can see now we are getting very close to full utilization of the cores. There's a bit of a spinny wheel. I'm actually losing some responsiveness in the machine. Because we're using the low performance cores for plugin processing, you can imagine that we don't have CPU so alive anymore to deal with my system interrupts of moving the mouse, playing with the keyboard, maybe refreshing the screen, although that's more GPU, but you know what I'm saying. We've used up those resources which were spare and available, but we are getting a lot more plugin work done. Let's try number 7, and that's where I get the overload. And run it again, you can see 6 is reliable. Now that's twice the number of these really heavyweight Abbey Road programs compared to what I was able to run before. Now, if this was a lower cost plugin, you can imagine there might be another 20 plugins that you could run that you weren't able to run before by setting these settings. Some of these things that we saw earlier weren't making an obvious difference. So if we go to the preferences, audio preferences, the process buffer range didn't really make a obvious difference, but if we apply it now, it won't run. I've done quite a bit of testing on this. Let me do it again for you. It's not going to run. And set that back to the large buffer range, and now you're going to find that it it does make a difference, or where we're in this ability to spread the load over all of the cores. So again, we're running. I am convinced that the best setup for playback performance is the one I'm showing to you now, which is on an M1 machine. You open up all 8 cores to the playback processing, you set a large buffer size, and you prioritize the multi-threading option to playback only, and sacrifice the performance of the machine and the reliability of the machine as you overdub and hit up with more live input to software instruments, which obviously in this situation we're not doing because we're in mixdown. So finally, I want to bring together certain things in conclusion. First of all, we've found that Logic in terms of performance is a dynamic machine in the same way that audio is dynamic. Because we are automating in our mix and we might be turning on routing through automation, really our CPU needs to be dynamic. We need headroom in our CPU capability. Otherwise, a session that we might start in real time at some point during the session, as we try and do something extra within our plugin resources, we might actually have a system overload. So that's the first thing. It's a dynamic process. Secondly, we found that the M1 system is incredibly thermally efficient, and because of the peak nature of Logic's requirement for CPU, although we do have spikes, we're not really heating up the CPUs. We've seen a maximum of maybe 60, top 70% CPU utilization. This leads me to the suggestion that if funds are tight, the MacBook Air is probably still a really good choice for Logic. The difference between effectively RAM being the same, if you compare a MacBook Air M1 to a MacBook Pro M1, really the difference is the Air has no active cooling. We find that even when we're having unstable Logic performance, we're nowhere near that thermal limit, and so I would suggest that a MacBook Air M1 would be a very, very good choice for running Logic. Now, I'm not saying that you shouldn't put 16 gigs in it. I'm still a firm believer that having the memory that does make a difference. If you were making a pound for pound comparison for Logic, then a MacBook Air with 16 gigabytes is probably the same kind of price as a MacBook Pro with 8 gigabytes. And so go with the Air and put a little bit more memory in it, and your buck is doing a better job for Logic. In terms of the new M1 Mac Mini, that has a cooling architecture quite similar to the MacBook Pro. So really the MacBook Pro and the Mac Mini M1 are both really good examples of the best we can do in terms of cooling. I would love to see comments from you based on what plugins are you using, what's your favorite stuff, or what do you find to be the biggest bang for buck in terms of CPU utilization, what's your most efficient plugin that's your favorite, what is your most inefficient hungry plugin that's your favorite. If this has been helpful, please subscribe to the channel so that you keep up to date with whatever else I do videos of next. This was all about CPU utilization. I will put in a link for you here that will show you more about memory utilization. Finally, let's keep mixing and keeping it real. I just think we need to be really careful of Logic demonstrations on YouTube where you never hear any audio and nothing is happening for real. We've learned actually Logic can be a really interesting beast when you don't route anything anywhere. Okay, see you next time.